Groups and inverses. Let M star be a monoid with identity E. An element A in M is called invertible if there is an element B in M such that A star B and B star A are both equal to E. A group is a monoid in which every element is invertible. Groups appear so often in mathematics that it's worth taking a few extra moments to write out the full definition of a group explicitly. So a group is a pair, G star, consisting of a set G together with a binary operation star satisfying one associativity. For all x, y, z in G, x star y star z is equal to x star y star z. 2. Identity. There exists an element E in G such that for all x in G, E star x and x star E are both equal to x. And 3. Inverse. For each x in G, there is y in G such that x star y and y star x are both equal to the identity E. If y in G is an inverse of x in G, we will usually write y as x with an exponent of -1, and we pronounce that x inverse. So we have y equals x inverse. So x star x inverse is equal to x inverse star x is equal to E. And of course here we're assuming that x inverse exists. In a group, for every x, x inverse will always exist. Recall that the definition of a binary operation already implies closure. Some authors will explicitly mention closure as one of the properties that a group satisfies. So closure says for all x, y in G, x star y is in G. A group is commutative or abelian if for all x, y in G, x star y is equal to y star x. Let's look at an example. Is the commutative monoid Z plus a group? Yes, it is. The inverse of any integer a is the integer -a. Another example. Is the commutative monoid n plus a group? No. For example, the natural number 1 has no inverse in the set of natural numbers. In other words, the equation x plus 1 equals 0 has no solution in n. There is no natural number that you could add to 1 to get 0. Is the commutative monoid Z together with multiplication a group? No. For example, the integer 2 has no inverse in the set of integers. In other words, the equation 2x equals 1 has no solution in Z. There is no integer that you can multiply by 2 to get 1. A rational number is a number of the form a over b, where a and b are integers and b is not equal to 0. We identify rational numbers, a over b and c over d, whenever a times d is equal to b times c. For example, 1/2 and 3 over 6 represent the same rational number because 1 times 6 is equal to 6, and 2 times 3 is equal to 6. We denote the set of rational numbers by Q. Notice the special font we use to indicate that this is the name of a special set, specifically the rational numbers. So we have that Q, the set of rational numbers, is equal to a over b, such that a, b, and z be non-zero. So again, in words, Q is the set of quotients a over b such that a and b are integers and b is not 0. we identify the rational number a over 1 with the integer a. In this way, we have that the set of integers, z, is a subset of the set of rational numbers, q. We add two rational numbers using the rule a over b plus c over d is equal to a times d plus b times c over b times d. Note that 0, which is 0 over 1, is an identity for the set of rational numbers together with addition. Because a over b plus 0 over 1, by our definition, is equal to a times 1 plus b times 0 over b times 1, which simplifies to a over b. And 0 over 1 plus a over b is, again, by our definition, 0 times b plus 1 times a over 1 times b, which again simplifies to a over b. As an exercise, you should show that the set of rational numbers, together with addition, is a commutative group. We multiply two rational numbers using the rule a over b times c over d is equal to a times c over b times d. Note that 1 equals 1 over 1 is an identity for q times. Because a over b times 1 over 1, by definition, is a times 1 over b times 1, which is equal to a over b. And 1 over 1 times a over b, again by our definition, is 1 times a over 1 times b, which is equal to a over b. Now, 0 times a over b is equal to 0 over 1 times a over b, which by our definition is 0 times a over 1 times b, which is equal to 0 over b. And that's 0. In particular, when we multiply 0 by any rational number, we can never get 1. We always get 0, so we can never get 1. So 0 is a rational number with no multiplicative inverse. It follows that the set of rationals together with multiplication is not a group. However, 0 is the only rational number without a multiplicative inverse. As an exercise, you should show that q star together with multiplication is a commutative group, where q star is the set of rational numbers with 0 removed. When multiplying two numbers, we sometimes drop the dot for easier readability. So we may write x dot y simply as xy. We may also use parentheses instead of the dot. For example, we might write a over b dot c over d as a over b in parentheses next to c over d in parentheses. Whereas we would probably write a times c over b times d as ac over bd. We may even use this simplified notation for arbitrary group operations. So we could write a star b as ab. However, we will avoid doing this if it would lead to confusion. For example, we will not write a plus b as ab. That would be confusing.